Okay, well, welcome everybody to this Raspberry Pi Foundation Computing Education Research Seminar. As you know, if you've been before, and it's lovely to see regular faces, we're running a series on cross-disciplinary computing, which enables us to bring in, some really gorgeous topics, really broad. And we're running that until November. And this is the third seminar. Through this series, we're exploring the interactions of computing with various aspects of learning and life and considering what computing education looks like in different contexts. And now I'm absolutely delighted, so excited really, to be able to introduce Yasmin Kafai and Elaine Griggs to give us this seminar, which is entitled Building New Clubhouses of Computing, Introductory Equity-Oriented Computer Science with Electronic Textiles for High School Students. All the elements of that title fill me with great anticipation. So Yasmin is the Laurie and Michael Milkins President, Distinguished Professor at the Graduate School of Education, University of Pennsylvania. That's a mouthful for a job title. While Elaine is a computer science teacher at the Pembroke High School in Pembroke, Massachusetts, and a facilitator for the Exploring Computer Science curriculum.
Thank you, Sue, very much for this wonderful introduction and the opportunity to talk about this work. And I also want to thank Elaine Griggs that she, as one of the ECS teachers and facilitators who was involved in the project, was able to share us. We just had a week of intense professional development, and I think just after school finished, so a lot of people are ready for vacation after a long and hard year in school, like many of you had. And so what we want to talk about, and we alternate between researcher and teacher, so you'll get two perspectives of electronic textiles, is to the new clubhouses of computing. And I'll say a little bit more about this in a moment on where this idea was coming from. Then Elaine will actually talk about what's a stitching the loop unit, the electronic textile unit in a classroom, what's a project, what the curriculum is, what her experiences with it. And I will present some results from research studies we have done on the learning which happens there. And Elaine will also focus in on the portfolio assessments which we have developed for this computer science activity. And then we have a few questions for the breakout discussions and meet with you after that. So that's the plan for today. And I mean, I obviously make reference to a book which many of you are probably familiar with, Jane Margolis and Alan Fisher's Unlocking the Clubhouse, where they were some of the first to really highlight the challenges computer science education had in recruiting. The particular book focused mostly on undergraduate education in the 1980s and 90s. What we are talking about is actually something which is happening right now in K-12 education, but I think this is probably a phenomenon over the last 10 years that computer science education is moving into K-12. Before that, it really wasn't part of the larger agenda. There is a frameworks all over the world, also in the United States, as well as in the UK, but also in Asia. It is truly, I mean, a global phenomenon that this discipline is now entering into schools. And many curricula activities have been developed. Right now, there's a big focus on AI education. But in the United States, Exploring Computer Science was actually one of the first projects long before there was a recognized need to bring this into schools, to offer a year-long introduction into various topics of computer science, because what Jane Margolis, Joanna Goodegale Chapman, and others observed is States, and in particular in those schools where underserved students from underserved communities were going, they had absolutely no opportunity whatsoever to find out about computer science. So code.org has picked this up and created and made available a lot of curricula. It's right now impossible actually to provide a list on what's available, because nationwide in the UK, you also had actually earlier than in the United States, a nationwide initiative to start computing. But the reason why we started looking at electronic textiles and not robotics or games, which are very popular, and I'm guilty as charged of promoting game design for learning computing, is because we wanted to kind of show something else. And the credit here really goes to Leah Beakley, who at the time was a graduate student with Mike Eisenberg at the University of Colorado, Boulder. And when the Arduino came out, she came up with the idea of, you see actually some of the examples of the early prototypes of how she customized the Arduino to make it adaptable for sewing, computing microcontrollers, sensors, and actuators, like you can see here, with conductive thread into clothing. And 15 years ago, this was quite a bold idea. Google Glass, Apple Watch, all of those wearables, which are very familiar now, actually hadn't come around. So people thought this was still kind of very esoteric. But the Lillipad Arduino, and there are many other platforms now. There is Adafruit Playground, there is MakeCode Play, there are many other microcontrollers which allow you to do the very same thing. But Leah also conducted a study in 2010 by looking at what people were doing with the Arduino, which had become very popular, and then what people were making with the Lillipad Arduino. And one thing she noticed, when you went online and just Googled it, you were encountering a very different set of programming projects. On the upper part of the screen, you see some examples of, the robots, the cars which people were making. And on the bottom, you see some of the examples of electronic textiles. And then she and Benjamin Marco Hill looked at who was making what. And she found that most of the Arduino projects were posted by men, whereas the majority of the Lillipad Arduino project were posted by women. So, and I think this is where also the title of this presentation comes from. She said, maybe if we want to open up computing, remember this was 2010, let's not just look at the existing clubhouses and invite women and minorities into gaming and robotics. Maybe we should also open new clubhouses, like for electronic textiles and others, where people can engage in computing and make projects, but which look very different from what we usually associate with those activities. So what's special about electronic textile, it's actually an interdisciplinary project. So it's not just computer science, it involves crafting, low-tech materials like textiles, low-tech practices like sewing, even though soldering could also be considered a low-tech practice, but it's usually different else. And what you see here is one of the wristbands, one of the first projects where students learn about making electronic circuits, but by stitching them with conductive threads. But then it also involves the familiar coding, because the circuits which students create are not just functional, meaning they turn on or off, they're also controllable. And so the Lillipad Arduino provides a language for where you can control essentially the actuators like LEDs and the various sensors which can be connected to the microcontroller. And then you also craft, actually. You work, more in the arts, topic areas which are not typically associated with computer science. So this was the idea of kind of bringing kind of computing into new clubhouses. And this was actually a quote which Mike Eisenberg unearthed, and which I find always very nice to remember, that many of the origins of computing go back to textiles. The analytic machines, this was a saying by Ada Lovelace, that the algebraic analytic engine weaves algebraic patterns just as the jacquard loom weaves flowers and leaves. So electronic textiles have a very famous history in computing, which has often been forgotten because most of the reference hark back to the Second World War and other initiatives. So that is kind of the history on where that all came from. And I want to hand it over now to Elaine to talk a little more about what it actually looks like when electronic textiles move into schools from the research lab, from the design table into a classroom.
Let me introduce myself. My name is Elaine Griggs, and I teach in the high school computer science classroom. We, like Yasmin just said, we did just come out of an intensive week-long PD for E-Textiles, which was my second summer, and that's how I facilitate ECS, Exploring Computer Science, for the last 10 years. And it's so amazing to be involved in this PD to implement the E-Textiles in the classroom, because we do have this level of support. And I was talking to Yasmin earlier, and I did try to implement E-Textiles in the classroom prior to the beginning of the formal PD. And I've been so much more successful with the PD and with the support of other teachers. And implementing this into the classroom has been a huge success with the students. The buy-in of computer science, my numbers kind of started to drop during the pandemic because of not really being able to do hands-on projects, which the students really were asking for. So once we implemented E-Textiles into the curriculum, students were literally asking, can we make something? Was one of my first questions in my ECS course. And we started off with, they start off the project. So ECS with the E-Textiles unit is project-based. And this is actually the second project that's on my screen now, is the wristband project. And prior to this project, we make a simple paper circuit using copper tape. And there's two different projects there, the e-card, and then what's called a mood lamp, which you can use different materials for, but it's basically another paper circuit. And
we cannot see your slides. You have to share your screen.
You can't see my slides?
No, you went out of presentation. You have to go back.
Oh, okay. Would you want to show the video now then?
Yeah, let's show the video.
Let's show the video now, and then I'll wrap up.
So to give you a better idea on what this all looks like,
yes,
we have a short video.
Programming, I've never done anything with computers in general.
Because I thought it was going to be like all about computers and stuff. Yeah. But it's not.
I thought it was going to be a little bit harder to do.
At first I thought you had to be really smart to code.
The E-Textiles unit covers a series of different projects. Each one builds on the next. students start out by making simple circuits and then eventually making parallel circuits with switches and computational circuits that they can program in customized ways. The programming includes a lot of challenging concepts, basic sequences, embedded conditionals, Boolean statements, mathematical operators, using sensors, and thinking through the logic of how to program those sensors.
It's not just crafting, it's sewing combined with circuitry. I love what you might call the hybrid nature of E-Textiles.
To see the possible connections between crafting, computing, and engineering.
Our E-Textiles unit seeks to bring making into computer science classrooms. We want to broaden who is participating in making in computer science. We want to deepen their learning by providing meaningful challenges to students. And we want to diversify who is making and what they are making. We're doing this by focusing on student-driven handcrafts.
The electronic crafting projects are not so much about teaching students stitching. Involves a lot of problem solving and thinking about procedures and steps, which I think connect very closely to thinking about computing and procedures.
But it's that transformation from their original ideas to what works and learning the skills, both programming skills and circuitry and crafting and all of those ways that those interweave.
It's usable. You can take it home with you.
Kids
lunch
come
that
in
I've
at lunch
never
that I've
seen
never
ever.
seen ever outside of the classroom without me asking them to. They just come because they want to do extra work or they want to make sure their project works.
I like to do challenging things.
So, Elaine, over to you.
Yeah, that's a great video. And that video closed with, maybe you want to share your slides because I dropped out of the sharing. That video closed with students reflecting that they want to move on in computer science. And that's really what I've found as well. Students who are able to do these projects have real personal buy-in. I'm also seeing students come after school. I just want to finish this amount before class tomorrow. Like, I want to just get this part sewn on, or do this circuit path, or do this amount of the programming, or I was hoping you could help me with this programming this after school just before class tomorrow. Like, I want to be in a certain place for class tomorrow. And you are seeing students who aren't typically coming after school to spend extra time when they're working on this project, because it is personal. They do get to take it home. My students took home their paper circuits, both projects we did with paper circuits. And I let my seniors take home their wristband in full, but the students do get to take home the wristband, just not the lily pad. So all students do get to take it home, but just not running on the circuit playground. So my students really are asking for these hands-on projects and very involved in these e-textile projects.
Okay, yeah, so here's an overview of the 4 projects. By the way, you can go to the Exploring ECS E-Textiles website and download the curriculum, a material guide, and all information which we provided to the teachers in order to implement these activities. One thing I want to give you some idea. So obviously we have not just done this in Elaine's classroom, but in many other classrooms. So to show that the project is successful, not just in teachers who are very engaged and familiar. And as part of a larger study, we actually ran it in 16 classrooms. This gives you an idea over the last several years on how we focused on different aspects and understanding what is happening in the classroom, what teachers are doing, what are students doing, and we'll talk in a moment actually also a little bit more about the portfolio assessment which we created as part of this activity. So here are some background information for those of you who are not familiar with exploring computer science. It's predominantly in public schools and in schools which have a very high percentage of minorities. So these are the schools usually who do not have computer science or the resources. These are demographic based on American standards, like, you know, providing lunch. To show that it's possible to do these kind of projects also in large classrooms with sometimes up to 40 students. And one thing we did a survey where we asked students about their confidence, their fascination, their value, their thinking about computer science. And what we found is that lo and behold, I mean, there were significant changes. And these were, except for the value of computer science, not based on differences between gender or any racial groups. I have to say the large majority of students are Hispanic or African American, so we don't have the typical comparison of Caucasian students here. So I think that shows that what Elaine just illustrated, that the students become more confident, more interested, and perceive, I mean, computer science in a larger way. And it's also independent of kind of the home language or family education of students. Another thing we did as one of the last projects, which the students entered, it's called the Human Sensor Project, where they can design an artifact. And then when you squeeze, the lights come. We had teachers actually, this is a coding rubric, which you see here, evaluate what kind of coding, what kind of circuitry and design and crafts. And I want to point out that we give half of the points to design and craft and not just the coding to balance it out. And what we saw that this is an example of what the coding rubric looks like. It's, by the way, published in the curriculum, so you can download it from there. So to give different points depending on how many components the students and how complete the components are implemented. And what we saw in the large-scale study, which we implemented, is that, not surprisingly, that the design and craft, most students accomplished very well, as well as the circuitry. I want to remind you that by the time the students do the fourth project, the Human Sensor Project, they have now the fourth time actually implemented a design circuit. And this is also, which explains that they have get such better scores on circuit design than the coding, which comes in the last two projects. So we can see that students actually, as part of the curriculum, not only kind of learn about circuit design, which is part of science or electrical engineering, but also about the coding, even though there is still room for improvement. So overall, if we look at what we see is that students become more confident, they become more interested in CS. And another aspect which we saw of those 15 teachers who implemented the curriculum, about half of them have actually done the project more than once. And for many of you who work in classrooms, this finding is probably not surprising. Teachers with experience actually have students who do better on those scores because it makes a big difference in how students get introduced to the findings. This is a finding which you see in many other STEM areas in science and math, so it shouldn't be surprising in computer science. The teachers who have a prior experience also have a positive impact on student performance. So I want to hand it over. I can just run Elaine through the slide and talk a little bit about the portfolios which we did. I have a paper published where we designed a pre and post test. And then I decided this really wasn't appropriate for the unit. And so we looked that some of the AP principals actually use portfolios. And so we decided to come up with a portfolio activity where students document their project. And here you see some of the writing which students do. So they take photos and they say a little bit on how the portfolios are implemented in the classroom.
Yes, I really, the digital portfolios have made a big difference in my classroom. As Yasmin just mentioned, the AP Computer Science Principals does use a portfolio. So this is a great preview for that too, and a great experience for the students. I've had my students even go on and expand their portfolio to use for college applications. I have them do other things with their portfolio, but for these projects, it really does allow the students to communicate and reflect on their design and their programming. And the steps for the design build up through the projects. So they're able to reflect as they go through the projects and add projects to their portfolio. Each project uses a rubric as well, and the rubrics are important for both the student understanding and being able to work with them on grading. From a teacher perspective, the rubric really does put everybody on the same page. And the rubric is part of the ECS unit on E-Textiles. ECS works with rubrics in every unit. So this is consistent for the students as well. And their reflection on the process really starts them thinking as computer scientists, really starts them thinking with computational thinking and the process, looking back over their process, talking about their mistakes, talking about then when they start talking about mistakes in design, they're talking about mistakes in programming. So they really naturally move to that debugging and incorporating mistakes as part of their learning. So this hands-on way of moving from a design aspect, using materials, using crafting, and then the collaboration in the classroom when given the time to have these conversations and learn from each other has been really surprising. After coming from robotics and gaming and doing these kinds of projects myself, where it is high collaboration, E-Textiles just brings this additional project-based unit into the classroom that kids have real buy-in on. They're able to, not always with a robot or even a game, sometimes they can, but not always do they really get to express their own interests in those types of projects. In these E-Textile projects, students can really express their own interests. I've had boys make like football patches using sports insignias and different types of sports they combine in here. And then this year, I had 100% of my girls move on to additional courses. And they asked, are we going to have these types of projects in the additional courses? And I have worked some projects into all courses now. And they really have been interested, and they've taken good ownership of the digital portfolio. They're a little hesitant on the digital portfolio at first. That's a little, that takes them, because they're doing this in parallel, right? They're learning the process, the design process, the crafting, the coding, and learning how to document that. And I think that's a big step for a college preparation course. You do so much documentation in college that this has become a really important part. the portfolio. So they've done really well with it, and it's allowed them to have that parallel reflection and reflection on their collaboration and seeing their ideas come to life.
Yeah. As part of the curriculum, reflection prompts are actually included on a daily basis. So students are collecting the images you just saw here and the code examples on a daily basis. And at the end of the unit, put the portfolio together, because we found if we ask students just to work on their projects and then at the end to document everything, they didn't have that information. So this is part of the process. And I'm lingering on this quote because when I read this, I was first upset. You know, this is a computer science unit, and the student is just reflecting on how, I think it was he or she improved on his sewing. And I said, okay, that is probably not what I would want as the outcome. But, you know, this was actually before COVID. Now sewing masks, it came actually really handy that students had the skill. But I think, you know, it's this, what we wrote a whole paper on this whole computational communication. Often when we talk about computational thinking, we just focus on the coding, the writing the code, but the ability to actually talk the tech language and to communicate and to talk about code, about documentation is as important as the ability to actually write the code. And we all know that nobody really likes to document their code. So the portfolios kind of capture this process where students not just list the code, but also explain what it means and where they made changes in their projects. So the portfolios were an important part of not just making these artifacts, whether it was the wristbands, the collaborative mural, or the human sensor project, but also to kind of talk and document the computational thinking practices. So, and I think we're coming at the end. I mean, there are, when you go to the Explore Computer Science website, there are more papers on different aspects of the portfolios, of the coding, of the mindset changes which students experienced as part. But I think it's a good time point now. I don't know whether there is questions in chat, maybe where we break into the breakout rooms. And these are 3 questions which we have for your consideration. One of them is, can you think of other examples for other clubhouses of computing? You know, E-Textiles is just one example. Have you, in your experience, maybe come up with other ideas which go beyond games or robotics, where students can explore computing and get introduced to the wide array of applications there are? A second question we have for you is, you know, bringing something like electronics into your classrooms or into your research. What do you see as challenges and opportunities for these type of activities, which definitely look very different from kind of designing scratch programs or even working sometimes with robotics kits? And finally, I mean, what kind of the things you heard today about the assessment, about the type of projects which kind of emphasize aesthetics and individual expression, could you take back into your classroom or research? So I believe we can put these questions into chat. And then you are being magically whisked into the breakout rooms, and we'll see you back in 15 minutes with questions, comments, challenges, and you have. We're looking forward to it.
Great. Well, before that, we can give you a big round of applause or virtual jazz hands or whatever we do electronically. Thank you so much, both of you, for a really interesting talk. That was loads in there to take away. Well, thank you very much again for the talk. And now we're going to take questions or comments from the breakout rooms. I saw that earlier, John, is he still here? John had a question about, do you want to say your own question, John? Or
Yeah, no, it was really because I mentor EPQ, which is extended project qualification, and the kids kind of decide their own agenda. They design their own project. And I didn't know whether there was a way of taking what you've done and instead of presenting it as a set project, present it as a problem, and then they've got to kind of react personally to that problem. So there's a specification in the problem itself, but then they kind of come up with their own different solutions. It just adds that little bit more kind of ownership, I suppose, or self-motivation or you know, self-direction to it. That was it. That was all I was trying to get at, really.
Yeah, I love that problem solving put on the students.
So I think the question is, are they restricted to those projects that you set up already, or can they? Is there an opportunity for them to freely make something that they're interested in?
No, I think the 4 projects are there because there also is a material requirement. I mean, so we need to have the materials available for everybody. But what the students are making, as you could see, in terms of cards, wristbands, or human sensors, varies absolutely widely. I mean, whether they make 3-dimensional stuffed toys, whether they use clothing or anything. It actually also, maybe Elaine can talk about this, poses quite some challenges for teachers, because even though the students all get a microcontroller and a certain number of LEDs or sensors for their projects, they all decide to kind of to design their own circuits and make their own artifacts. So none of the artifacts look exactly alike, which also means the number of bugs and problems which can occur multiply. So not everybody does make exactly the same wristband or the same human sensor project. Elaine, how do you handle that in the classroom?
Right, and that's what some of the questions are coming through about, like materials-based questions. I mean, it's a challenge to either hand them out all the materials they're going to say need and then choose from there, or allow the students to choose their materials more freely, which I do. So the students really choose their materials more freely, which allows them to have more openness in their response to what they're going to make. But yeah, there's the challenges in the materials are probably the primary challenge, and making some decisions by the teachers. There's a lot of ways to handle it. So each teacher, I would say, does something different, and then has different results too. And they have different spaces in which to work. Like I have a big table and my computers are around my room. So I think it's very different depending on the space you have to teach in too, as to what your solutions are with the materials. I do give roles to my students. So someone mentioned cleanup. We have cleanup time. We have like a materials manager within a group of 4. So that person would like go to the closet and then come out with a bin of 4 kids' work and keep that organized on a shelf. So I have a lot of like movement that I do prescribe by roles.
Yeah, I mean, essentially for the E-Textile project, you're turning your classroom into a mobile makerspace. Because teachers work in their classrooms. I mean, they do not go into maker spaces where you could house all the tools and materials. And at the end of class, all the stuff has to kind of be packed up and organized and stashed away for the next meeting, or where the students keep it in bags. So somebody asked about cleaning. I mean, technically, I think you can wash the, well, you probably shouldn't put it into a washing machine. I mean, that probably doesn't fare too well. But the conductive thread can easily be washed. That doesn't go away. It's a little bit finicky. The metal in it often breaks, and often the sewing in the beginning is very loose. People don't have a very connect stitch, so that can cause some problem, but it's not impossible. There are earlier versions of the LilyPad Arduino where you could a snap-on version where you could lift off the microcontroller, and then the sweatshirt or any wearable was actually washable. So I probably wouldn't put the microcontroller into a washing machine.
That's great. Okay, now we've got loads of questions now. So I'm going to go through them in order, or comments or suggestions, answers to the questions. So I'll start with Hamad, and then Catherine, and then Saman. So Hamad, you just had a general suggestion of a project, I think.
Yes, it was just a comment on another example of Clubhouse of computing.
What was it?
Oh, right, sports science, basically. So applications in collection of data and then analysis for improvement in diets and performance, just at a classroom level.
So is that something you're doing in the classroom level?
No, it's just a suggestion as an example that was discussed in detail in the breakout room.
I think I've seen a number of those projects, and I think they're very, sports and wearables, whether you include sensors in shoes, to record speed or other ways, are other great examples on how we can expand and show students the variety of applications. And those are actually used in professional contexts. People, so it's not just, make believe. People actually use this kind of the data you collect to help people improve their performances. The physical computing tools you use are probably much more low tech and not as refined as what's used in professional setting, but it comes fairly close to the same ideas.
Lovely. So let's move to Catherine, who had a particular question. Catherine, you there? Oh, there you are.
Yes, I am. Thank you, Sue, and thank you, Elaine, and thank you, Yasmin, for a fascinating talk. I was thinking about question 2 that you mentioned and the opportunities and challenges for using e-textiles in the classroom. It sounds like a really exciting activity, and also one with the potential for lots of chaos potentially, perhaps. You've touched on this already a little bit in terms of assigning roles to students, but I wondered if you could say a little bit more about how you saw students working together or alongside each other in the creation of their projects, or what kind of peer interactions you observed in those.
They really, like you just mentioned, can work together on a project, and like pair programming, where one student is programming, one student is helping programming, or one student is crafting, one student, so more all on one project, or parallel, where each student has their own project and work together like that. I would say in my class, they work more parallel on their own projects. And that's probably by choice of that's a student-centered kind of how they want to proceed. If students want to work together, they can sometimes do that. But otherwise, the chaos I do manage by the roles and grouping students and grouping the materials.
There, of the 4 projects, 3 of them are individual: the card or mood lamp, the wristband, and the human sensor. But the mural is actually a collaborative project where all the students, when they're getting introduced to coding, contribute a patch essentially to the mural, which then is displayed in the classroom or elsewhere. So that was intentional also for the most difficult part, to have students work together to repurpose their wristbands and to make the mural. Another thing which we often observe, we see this also in the professional development with teachers, when students are crafting, I mean, there is a lot of chatter and not everything talk is about code. There's also a lot of, on the videos, I know we find out a lot of things which happen in school between students and we probably shouldn't know about. But I think it's what's been observed in quilting circles too, when people they're all busy working. So there is a chaos, but it's also focused on making artifacts and students see to the right and left. And we observed a lot of peer assistance where students help students with their sewing or point out problems, how they can fix their code, which happen quite naturally in this context. So yes, there is chaos and lots of materials are floating around, but it is also managed through the roles Elaine said, and through this kind of peer support, which happens in around when students sit together at a table, but also across the classroom. Often teachers also say explicitly, the students know how to do this. And if you have a question, go to the student, he or she can help you fix that particular problem with your circuit or your code.
So they're helping each other. So there's a few more questions. So Saman had just a comment on challenges, and then we'll go to Bobby's question after that. Saman, are you there? I'm trying to see. There you are.
Hi, yeah, I'm here. It's just that these are more of a comment, more like comments.
Yeah.
And we were utterly fascinated by this presentation, and yeah. There wasn't a question from my...
Oh, right, yes. And you put that it might help with gender balance.
Exactly.
Which was, we really struggle with in the UK.
Yes.
Bobby, you had a challenging question.
Yeah, perhaps not. Thank you, Elaine. Thank you, Yasmin, for a very nice presentation. We were quite interested in the term clubhouse, and maybe this goes a little bit back to the theory, and I've read a lot of the computer clubhouse, but if our question essentially is, if you're imagining these applications of e-textiles and other things also in formal school curricula, why use the term clubhouse and not application?
Oh, that was just really a reference to Jane Margolis's book. I mean, when she noticed on how computing cultures felt like clubhouses, and a large number of women and minorities actually didn't feel they had access to those clubhouses. And we all know that tech communities are very exclusionary through their language. They signal whether they're kind of experts or not. And so I think the notion of a clubhouse is that it also invites certain people in, and also certain activities. And Leah's observation was in a lot of maker cultures, how prominent all the robots, the electronics, the car races were as examples of what could be made. And she said, where is the arts and craft? Where is the knitting, the different materials? And material science is a fascinating area on what's happening in engineering. And why are those not the activities featured in the clubhouses of computing? So yes, there is, I mean, a reason on why we call it the clubhouse, because clubhouse signals membership and, you know, who is part, and it's not just the who is part, but also what is being part. And so I think this is an intentional effort to say this is also part of computing. And nowadays, I mean, you know, 15 years ago when we started out working with Leah, there weren't that many applications. It was still very much in a laboratory space, but now wearable computing is out there in the world. I mean, so the idea of putting things into clothing to record data, like one of you suggested for sports, is not something so outrageous. Now we have actually the tools and materials which are accessible also to K-12. I mean, the idea of wearable computing, Maggie Orse at the MIT Media Lab made the music jacket in the late 1980s, has actually a long history. So the precedents are there, but now it's part of computing applications. And so I think the clubhouses also need to be created for that.
Thank you.
I always say, you know, it's like sometimes in computer science, like it's everybody's reading Shakespeare, not realizing there's a whole rich set of literature out there. And we need to kind of identify all those other authors and topics to make computing as rich, showcase it to students as rich in activity, especially in K to 12, so they can make informed decisions on where they want to go later.
Right.
There's nothing wrong with games and robotics, but it's not the only thing.
Brilliant. Okay. So there's lots of sort of comments. I'm just going to pick up on 2 questions I can see in the chat, specific questions. So Gitika, you've got a question, and then Randy. I hope I pronounced your name.
Yes. Hello. That's right. Thank you so very much for this session, Yasmin. So much to gain in, and yes, we would preferably like to use and start it at my classrooms. But I would like to know that which key stage is best to start with this.
So let me do a bit of translation, Gitika, because they don't have key stages in the US.
Okay.
So grades, and we'll try and translate. Grade 6 to 8 is key stage 3. 2 to 5 grade is our key stage 2. So what key stages, what grades do you
which age group, or we can ask that which age group is best for this kind of e-textiles?
You could start the early projects with elementary school. The stitch card, the wristband is for elementary, middle school. Now the curriculum, I just put the link into the chat, is specifically designed for early high school. So the last four years, I think ECS is taught from freshman 12, 13 to up to 16 or 17. So it was designed as part of an introductory high school curriculum. But I mean, I have done workshops with elementary, middle school students. And if you use like the BBC microbit, I easily think you can do many of the activities also with middle school students. That's just a fact of the American system. I mean,
yeah, no, I've done a bit of translation. I think elementaries we call primary and middle we call key stage 3. I think if that's right.
Yes,
that's great. And Randy, you had a question about hackathons, which I thought was something else to bring into the conversation.
Yeah, sorry, can you hear me okay?
Yeah, sure.
Yeah. So the idea is, and it was actually proposed by our robotics club, it was to try to recruit students who don't typically see themselves, either as robotics kids or as computer science kids. And so I didn't even have to prompt them. They thought that this idea of e-textiles would be a great way to be a little bit more inclusive. So I just threw that out there to see if has anybody done like a hackathon. And actually Elaine has been messaging me with great ideas for the paper cards. So just trying to brainstorm with people. I think a hackathon, we often think of them as just like kids sitting in front of the computer and just hacking away on code. And I wanted it to be a little more inclusive.
Actually, Penn, a University of Pennsylvania runs one of the largest college hackathons twice a year. And as part of I managed to get in, and I see somebody else has actually used the term Stitch Fest. And so as part of the hackathon, we brought in electronic textiles and had people make variables during the 2 or 3 days with different applications. And there is a paper which I wrote, and there's a documentation on how we organized the hackathon, what the rules were. There is a time-lapse video where you, I went to bed after midnight. You know, I didn't do the 24-hour or whatever 48-hour stint. So yes, we have actually done, there are many other examples where people do hacking for good or hacking for social activities. So yes, you can also make this around wear and care. That was, I think, one of the themes we had for one of the hackathons, to kind of showcase, again, different applications. And I put the link, I have it on my website. This is from we ran the hackathon twice as part of Pen Apps. So it was very successful and great kind of variable game controller interfaces, things which people kind of, there was a lot of sewing involved too, so.
Brilliant. I think I skipped over Bonnie's group, or Colin and Bonnie's group's question, which was about soldering. Do you want to ask that? We've talked a lot about sewing. Do you want to ask that one, Bonnie?
Yes, so one question that came up was whether it's all stitched or whether students would need soldering skills as well.
You don't need soldering, so you can either use with conductive thread, which is you have to learn how to sew, which is for many people a lost craft, but some actually do know this, use this in their families. So it's very interesting on how this brings in also family kind of connections, or like what Elaine also explained in the beginning, we sometimes for the cards we also use copper tape, copper tape, which is a little bit easier. And then you can also always use alligator clips, which are not permanent, but to test out things. The soldering is, is just a different technical skills which people are used more in robotics to kind of customize their beadboards or different connections, but you don't need any of that. So you just use the thread and you make multiple loops to make the connection really tight. It's a skill like soldering. You just for the copper tape, WeYi has done a lot in paper computing. So to use how you can use paper and copper tape to make really interesting artifacts. That's another interesting application. We don't think of paper as something in connection with computing, but to create big wall displays and really interesting artifacts. So paper circuits is a whole nother area where she also has designed controllers which go with that. They're actually on display in the Museum of Modern Art in New York, even in the shop. You can buy the kits for that.
Wow.
I was going to say that in our Raspberry Pi Foundation's all staff things, we all got sent copper tape. Here it is.
Oh yeah, here it is.
And did paper circuits, a whole staff team, everybody. Oh yes, there's Catherine's got hers up there. So the adults can enjoy it too.
And it's very popular because you get an introduction on how circuits. We use the sewing, so the students need practice in sewing. It's hand-eye coordination, which doesn't come easily. It's the same when you learn soldering. You also need experience with the tool and practice before you can really use it. So there's really not much difference, except we think about soldering as more technical than sewing. It's a cultural kind of stereotype.
We're coming to the end. I think some of the questions in the chat have been answered and some others are comments. I have one question for you, which is about assessment. So if you're doing this in the curriculum, and obviously it's really good for engagement and motivation and interest and confidence. And I saw some rubrics and things that you'd shown, but how do you try to actually assess programming skills, or are you just assessing circuitry skills, or what's your approach to it in the formal curriculum?
We're assessing both. I'm assessing, the recommendation in the curriculum is really about half and half. We are definitely assessing the programming part of it, and the debugging becomes natural after, as you go through the projects and they get harder. The students are really debugging from a space of wanting to get their idea to come to life. So they're more interested in debugging and getting their code to work. What I've seen is that they have a lot of interest in getting their code to work like they want to.
Yeah, so here's a rubric again, and so you actually do look at the code on whether it's working properly, on whether the requirements are fulfilled, whether it's commented in addition to the circuitry, and then design and craft. And the portfolios are yet another way where students essentially focus on what we call computational communication. So it's actually a key aspect of computational thinking, which drives a lot of the CS curricula. But the communication is that you're writing about code, that you're documenting your code, as you could see here. So you're actually articulating what your code should be doing. It's a statement. You're having the circuit diagrams and the images on how that's realized. And you're actually putting code and kind of also pointing out connections. And so for those, we also use rubrics to score them, to give feedback to students. It's, and I have published tests, where students can show that they can write the code. I think it's appropriate. This is an introductory curriculum. It's not an AP course, advanced placement in the United States, so that students get an introduction, as Elaine pointed out, into the portfolio writing, documenting code.
Go on, Elaine, sorry.
Yeah. So I just wanted to finish. We have done, tons. You heard mostly about the curriculum where how we designed this. We had a whole project on debugging by design, where we actually asked the students to make buggy projects which have problems, and then give them other students to fix. Because we noticed that students encounter a lot of challenges when making their electronic textiles. So we turned the table. We have a 2-week unit, which we have uploaded. It's an extension unit to the curriculum. So where you can teach students to make a hall of failure, to share all the problems which have come along their projects, and then make buggy projects. And we found actually in research that this significantly increases students' confidence in making their last project. And the last part is what Elaine also mentioned, that we're now working to train facilitators in electronic textiles, and working with all experienced teachers. So to find out, so we're much more focused on teacher learning right now than on student learning, which drove a lot of the first 10 years of doing electronic textiles. So what does it take for teachers to do these kind of projects? What are teachers' needs? How do teachers kind of create classroom community, promote mindset, and all of that? So there's a lot more coming out, which expands on how we think about electronic textiles as part of computer science education.
Thank you. Well, that's it's so fascinating. Your work has been going on for so long, and you're always developing it. It's a fantastic stream of work that you been talking about. So let's again say another thank you for a long Q&A, and thank you very much for the contribution. We really enjoyed it, and I think looking at all the comments in the chat, everybody's really engaged with it. So just some final points from me. We of course have a survey, and we want to make sure that these seminars continue to be useful to our audience. So please do fill in the survey and let us know what you've enjoyed. The link is there, and I think Diana might also circulate it. If you've got, as I said, we've got our Twitter handle. Do carry on the conversation on Twitter. We will be sharing, as we do with all of our seminars, the video and the writing a blog post about it. If you spoke in the Q&A and you don't want to be in the video, just drop Diana a line so that we can delete you, or not show you, sorry, not delete you. That's all on this seminar. So looking forward, we generally take August off because we find that a lot of people are on holiday. So we've got 3 seminars left in this series in September, October and November, the first Tuesday of every month. In September, we're looking at dance, ballet with Genevieve Smith-Nunes, who's local to Cambridge here. Conrad Wolfram is going to talk about mathematics, computational curriculum. And then our own Tracy and Rebecca are going to talk about computing education in non-formal learning. We've just had a paper accepted at ISA, which we was going to talk about there. So more to come, and then we'll be announcing the next series after that, which is a secret at the moment. So thank you very much for coming along. Really appreciate. In the UK, it's a very hot day. Well, it is in the south of the UK. I don't know if anybody's from the north of Scotland. So we've taken a break from the hot weather, and look forward to seeing you next time.